Time is 2:30, so let's get started here. Project number 1 is due on Wednesday at noon. Are there any questions before we get going? Okay. We left off on page 179 of the notes. So we've been focusing on ways to compare two probabilities of success. We talked about pi 1 minus pi 2, pi 1 divided by pi 2. Now we're going to look at something a little bit different called odds ratios that allow us to compare two probabilities of a success. And these odds ratios actually work by us rescaling the probabilities to begin with. So instead of looking at probabilities, we're going to look at odds of a success. And just to make sure you understand what an odds of a success is, let me get my red pen and stuff out. Basically, an odds of success is simply your probability of success divided by your probability of failure. All it is a rescaling of a probability of a success. That's it. It's just a rescaling. So we could have the odds of a success for group 1, call it odds 1. We could have odds of a success for group 2, call it odds 2. So for example, if the probability of success was 0.75, then what that says then is 0.75 divided by 0.25, which is equal to 3. 3 is the odds of a success. Outside of the statistics world, you hear people refer to this as 3-to-1 odds. We'll just call it odds equal to 3. So, in other words, the probability of success is 3 times as large as the probability of failure. How do we estimate odds? Well, we do what you might expect. Just put hats on the probability of successes. So the estimated odds of a success for group 1 is just simply pi hat 1 divided by 1 minus pi hat 1. And if you put what the pi hats are in terms of counts, you end up with the number of successes divided by the number of failures as the estimated odds of successes.
Doesn't make any difference if we interpret the odds as likely rather than as large?
Yes, because likely means probability. Okay, so you have to be very careful with your wording there. And that's why when we construct a likelihood function, we're essentially looking at the product of, if you think of it in the binomial sense, the product of probabilities. It might sound picky, but they mean separate things, and one could easily think you're meaning something else if you don't be precise in your wording. So, in terms of our contingency table, then an estimated odds of success for group 1 is just simply W1 divided by N1 minus W1. Okay, so some questions. What is the numerical range of an odds? So the lowest in odds could be and the highest in odds could be. 0 to infinity. Yeah. So there is no upper bound there. So again, an odds is just a rescaling of a probability of a success. So instead of going from 0 to 1, now we're going to 0 to infinity. What does it mean then for an odds to be equal to 1? Just to make sure you're following this.
No chance and same chance of having or not. Same odds of having or not. Or being 50-50.
I think what you're getting at, the probability of success is equal to the probability of failure.
Yeah, exactly.
So now we know how to calculate two odds of a success. And similar to what we did with the relative risk when we took the ratio where we looked at the probability of success for group 1 divided by the probability of success for group 2, why don't we just do the same thing with an odds? And that's how we form what's called an odds ratio. Odds ratios are used throughout categorical data analysis. We'll be talking about these pretty much every day from now until infinity, or until the end of the semester. So an odds ratio, I'm just going to call OR, for the lack of a better symbol, just odds of success for group 1 divided by odds of success for group 2. So if you put in all those quantities then in terms of the pies, this is what you get. And essentially, all you're doing, if I go back to my table here, the numerator is simply the product of pi 1 and 1 minus pi 2. So the diagonal, you can say, of the table. And then the denominator ends up being the product of the off diagonal, pi 2 times 1 minus pi 1. So that's an easy way to remember how to calculate that odds ratio. So then some questions. What is the numerical range of an odds ratio? 0 to what? Infinity. Again, yes. What does it mean for an odds ratio to be 1? The odds of success for group 1?
It's equal to the odds of success of group 2.
Yeah. Same for group 2 as well. So in other words, if you phrase it in terms of Stat 802 terminology, if the rows represent 2 treatments, there's no treatment difference between the 2. So that might be, essentially of interest, let's say like in a clinical trial setting where maybe you're testing a new drug versus a placebo. What does it mean then for the odds ratio to be greater than 1? The odds of success for group 1 are greater than for group 2. And then if odds ratio is less than 1, then the reverse is true. Okay. Well, how do we estimate the odds ratios? Again, where you see parameters, put hats on them. And that's basically it. And notice what ends up, so OR hat is my estimated odds ratio. Notice what ends up being is simply the number of successes for group 1 times the number of failures for group 2 divided by the number of successes for group 2 times the number of failures for group 1. So if I go back to my contingency table here, similar to what I had demonstrated before, all you're doing is taking the product of the 2 guys or the 2 counts on the diagonal and you divide by the product of the 2 counts on the off diagonal. If you think in terms of, if you're familiar with the idea of a diagonal in terms of matrix algebra. Okay, now this estimated odds ratio here is actually the MLE for similar reasons to what we saw for the relative risk. I think one of the cool aspects of this odds of an odds ratio itself is that notice we're just using one number to summarize essentially 4 cells of a contingency table. I think that's kind of cool. One number is basically telling you what's happening with 4 numbers essentially. And that's one reason why odds ratios are so useful. So the interpretation. Well, interpretation of odds ratio can be difficult for some students, at least before I put in some of these examples here. In the past, I think students had a lot more difficulty. I don't think it's as big of a deal since I put this stuff in there, but still students sometimes don't get it quite right. So let's spend some time making sure you get the interpretation correct. So here are 2 standard interpretations. You can use these as templates for your own and essentially always, like on a test or a project, get a problem right. Of course, I hope you think it's more than just a template and you actually understand why certain things are said in certain places. Okay, so number 1, the estimated odds of success are OR hat. So OR hat would be like a number, like maybe 4. OR hat times as large as in group 1 than in group 2. That makes sense. You're comparing 2 odds of success, group 1 versus group 2. And we're looking at times as large. Let's think of what we were talking about in terms of the relative risk before. So, if you ever have, and you'll see this as we go along here, if you ever have problems, thinking about what is an odds ratio, how do you interpret it? Again, just go back to the basics of it's the ratio of 2 odds. That's it. Okay? Now, sometimes, it's kind of arbitrary. What do you put in for group 1? What do you put in for group 2? Why don't we just flip-flop what the 2 rows are? Or equivalently, you could say it this way. Why don't we phrase this interpretation in terms of group 2 than in group 1? So what happens? Well, essentially, the 2 odds flip in the OR hat formula. Or equivalently, you could say the estimated odds of success are 1 over OR hat times as large in group 2 than in group 1. Okay. Now sometimes though, you might want to interpret the odds of a failure instead. You can do that. What you could do is just simply flip-flop column 1 and column 2 in your table and then do everything as we just did before. But let's say you just want to keep it in terms of the odds of a failure. Well, excuse me. So the odds of a failure now is simply, let's say for group 1, would be 1 minus pi 1 divided by pi 1. So just the flip of, or the inverse of what you have for odds of success. And then the odds ratio then for group 1 versus group 2 becomes the ratio of the two odds of a failure. And so look what you end up with here, 1 over the OR hat that we had before. Okay? So what are some interpretations then? The estimated odds of a failure are 1 over OR hat times as large in group 1 than in group 2. The estimated odds of a failure are OR hat times as large as in group 2 than in group 1, where I had to do that little inverting again. So you can see that there are 4 separate interpretations essentially that you could have of an odds ratio depending upon how you're looking at it. Odds of success, odds of a failure, or group 1 versus group 2 versus group 1, or whatever. And that's where I think where some of the issues come in sometimes for students for interpreting this.
So OR is also success, and 1 over OR is also failure.
Let's be careful here. So OR is a comparison of 2 odds of success. So you're looking at the odds of success for group 1 divided by the odds of success for group 2. Okay, so I wouldn't call OR an odds of a success. It's not. It's a comparison of 2 odds of successes. Does that help? Then you were talking about odds of a failure. Well, again, it comes back to the basics of what you're doing here. Actually put in here the 2 odds of a failures and take the ratios. And it just so happens, if I were to relate it to what we had when we were comparing odds of successes, it just so happens it ends up being 1 over OR hat. Okay? Well, what about confidence intervals? Well, OR hat is a maximum likelihood estimate. So, similar to what we've done before, we won't, but we could take our estimate plus or minus the value from the standard normal times the square root of the estimated variance of the estimator. We could do that. Unfortunately, that doesn't work as well as if instead we use some kind of transformation of the odds ratio. And just like what we did with relative risk, we're going to use the natural log transformation. This works good. So, instead we're going to work with the log of the OR hat that happens to have an approximate normal distribution with a mean of log of OR. And the estimated variance then ends up being basically 1 over each of the cell counts, sum them up. How do you derive that? Don't worry about it. It comes from the delta method, which is talking about appendix B. So then what we do is we form a confidence interval, a log confidence interval for the log of the odds ratio. Again, we take the estimator plus or minus the value from the standard normal times the square root of the estimated variance of the log OR hat. Again, we want the odd. We are really not concerned about the confidence interval for log of OR. We want the confidence interval for OR itself. So what do? Well, we use the exponential function, just like what we did with the relative risk. And so now this is the actual confidence interval that we end up using for an odds ratio. And interestingly, some research has shown that this is actually a little bit of a conservative interval, despite being called a walled interval. It's just due to this log transformation, it ends up making it just a little bit conservative. And then I have the question: what does conservative mean? Just to make sure you remember.
Likely to include the true estimate, the true parameter?
More likely than what it should in terms of the stated value to contain the true parameter. So if the stated confidence level is 95%, conservative means the true confidence level is actually a little bit above. Okay? Rather be conservative than liberal. Hopefully, though, you see one little small problem that could occur. What happens if you have a 0 cell count? You're going to have problems calculating that variance, right? So what can you do? Well, ad hoc solution would be maybe just to add a simple constant to that one particular cell, or what you would see more often done is add 0.5, let's say, or some other small constant to every cell. Note that when you do that, then your OR, your estimate of the odds ratio is called OR tilde, is changes, as does then the variance too. So you have to carry forward that a constant. And actually, in that same paper that I cited here, I guess Louis and Lin, they actually showed for some cases actually always using this constant adding, even when you don't need it, actually ends up producing a better interval. And so my co-author and I, we kind of debate about, well, do we always want to maybe use this, essentially this adjusted interval all the time, similar to like a Gresti-Kuhl, Gresti-Caffel? We decided, well, I didn't think the benefit was enough to warrant, its use. So that's why I decided just to not use that constant unless you absolutely need it, and when you have a 0 cell count. Okay. So let's take a look at an example. We go back to Larry Bird once again, and we come on over here to 10. So if I want to find my estimated odds ratio, remember my data is in C.table. So I just simply pull out the particular cell counts that I need. So the 1 cell count gives me my W1. The 2 cell count gives me my N2 minus W2. And so I just do that throughout the table. And here's my estimated odds ratio, 0.77. Sometimes it's useful, and you'll see this shortly. Well, I guess you have already kind of, to look at the inverse. And so my inverse is 1.3. We'll interpret that next. So on page 85 then, the interpretation, the estimated odds of a made second free throw attempt. Remember, a success is a made second free throw, are about 0.77 times as large as when the first free throw is made than when the first free throw is missed. Okay? Or alternatively, you can phrase it this way. I think sometimes too with odds ratios and relative risks, it's often easier to say the interpretation if your value that you're interpreting is above 1. At least that's my opinion. My co-author kind of disagreed with me, so we do both of them. The estimated odds of a made second free throw then are 1.3 times as large as when the first free throw is missed than when the first free throw is made. So compare that to the first bullet where I had made than missed. Okay, so remember what we talked about first when we saw this Larry Bird data, and that is, notice how his probability of success is a little bit higher on that second attempt when he misses the first, which is kind of counterintuitive. And the odds ratio basically says the same thing, as you would expect, because again, an odds is just a rescaling of a probability of a success. Now, this happened in this sample. This doesn't mean, though, would happen, let's say, the next season when Larry Bird was attempting the free throws. This is just based upon this one sample. And so that's why we use statistical inference techniques such as confidence intervals to make a judgment of, well, will this hold in general? Another way that you can interpret your odds ratio, too, is as follows, that I hadn't really focused on before. So the estimated odds of a made second free throw are 30% times larger. Key element there was the larger. Notice I'm not saying as large, I'm saying larger. When the first free throw is missed than when the first free throw is made. So all I'm doing is taking a little bit of a different interpretation based upon that 1.3 that we had there. Just like what we were doing with the relative risk before. So I'm not trying to confuse you by throwing all these interpretations out there. I'm trying to get you used to these interpretations because depending upon like what paper you read or depending upon what your interest is in interpreting your own odds ratio, this gives you some background of how to do it. Any questions? Yes.
So on that, would you, if you use the first interpretation, would you say 27% times larger if you flip the missed and made around as well?
Well, notice I did flip it.
But I meant for the, so when you say 30% times larger, when
Mhm.
the first is missed and the second is made, could you flip that the other way for a fourth interpretation as well?
You could say, let's see now. You could say 23% times smaller. I think that's what you're getting at.
Yeah.
So here are some incorrect interpretations. Circle the incorrectly there just to make sure you're getting it. The estimated odds of a made second free throw attempt are 1.3 times as likely. Notice the word likely there. We were talking about that a little bit earlier. I know it makes you want to use the word likely there, but you got to be very precise in what you say. Likely corresponds to probability. So here you are talking about probabilities, and then you're also talking about odds at the same time. And that is somewhat confusing. Also, don't replace the word odds with probability. So in terms of my original interpretation here, don't put probability there. Don't put the word likely there too. Okay? I have seen that happen. In fact, there was I don't think I ended up putting it in my book as an exercise, but there was about 10 years ago, a Lincoln Journal Star sports writer was talking about field goal kicking, and somebody had actually done some stuff similar to some research that I had done, and the Lincoln Journal Star writer was interpreting what this was interpreting the article that a article on a blog, I believe, which was interpreting an actual statistical research paper, and in between that those various interpretations, the Lincoln Journal Star writer was starting to talk about probabilities and likeliness of something, when in fact he was talking about odds ratios. And so I emailed the Lincoln Journal Star writer and said, hey, you can't do that. You're not interpreting it right, because somebody might think you're talking about relative risks. He never got back. Let's see now. So, this is comes with the relative risk discussion before. The estimated odds are 1.3 times higher. That's not necessarily true, or larger, because that is not interpreting everything correctly. You need to say 30% times larger, 30% times higher. So let's find the confidence interval then. So 95% interval, I find my estimated variance, as you might expect. I take 1 over W1 plus 1 over N1 minus W1 and so on. To find my estimated, to find my confidence interval itself, I use the XP function for the exponential part. Take the log of OR hat plus the value for my standard normal times the square root of my estimated variance. I do all the calculations, and I get an interval of 0.29 to 2.07. Okay, so you could also invert it too, depending upon where you're gauging your interests. So I could invert it to be 0.48 to 3.49. So this 0.48 here, how did I calculate that? I took what? 1 over what? 2.07, yep. And this was 1 over 0.29. Okay? Sometimes you get confused that, okay, when you're taking that 1 over that smaller number, you forget now that becomes the upper bound, essentially. Okay, so what's the interpretation? So notice I'm not going to use the word estimated here at all, because now I'm talking about the true odds ratio. I have a certain level of confidence associated now with what I think the true odds ratio is. So with 95% confidence, the odds of a made second free throw attempt are between 0.48 and 3.49 times as large when the first free throw is missed. Remember how I inverted the odds ratio? Then when the first free throw is made. Okay, so the key thing here is for Larry Bird, the value of 1 is inside this interval. So what that means is I cannot prove that indeed that first free throw attempt has any effect on the second free throw attempt.
I have a question about
Sure.
the interpretation of confidence intervals in general.
Yeah.
So you said we can talk about the CI in terms of the population parameter.
Well, I mean, confidence intervals for a parameter, which essentially is something that's a numerical summary measure of the population.
But the value inside, the value it's created around is a statistic.
I mean, here, look what's in the middle here. It's a parameter. And how do I find the bounds? That's where I use statistics. So, you know, the information that I get from my sample is what's used to find the lower bound and what's used to find the upper bound. The thing that's in the middle is always the parameter.
But then we want to say, one of the interpretations you gave was if we did the same experiment or the same stuff all over again, we expect to find them in that range, 95% all the time.
No, not that particular range. That second interpretation that I think you're talking about comes about something like this. You state, let's say you state your interval. Let's say it's 0.29 to 2.07. Then you would say for 95% of all similarly constructed intervals. What that means is that you go out and take a sample, calculate another interval. Go out and take a sample, calculate another interval. Go out and take a sample, calculate another interval. For 95% of those, I would expect my one parameter, in this case OR, to actually be in 95% of those intervals. My interval changes with every single sample. That's the key. And I think sometimes that's where the misunderstanding happens with using that second interpretation for some students, is that they think that 95% of my ORs are going to be inside that interval. Well, there's always going to be only one OR, okay? Because that's the parameter. Let's take a look at the polio vaccine clinical trial data once again. And just, I'm not going to go through all the calculations. We're just going to look at the actual numerical results. And one can actually calculate the OR hat to be 0.4. So the estimated odds of contracting polio are 0.4 times as large when the vaccine is given rather than the placebo. And that matches our relative risk interpretations that we were getting before. That the risk of getting polio is less for the vaccine group than for the placebo. You can also phrase the interpretation like this: the estimated odds of being polio-free are 2.49 times as large as when the vaccine is given than when the placebo is given. I'm sorry, make sure I said that right. The estimated odds of being polio-free are 2.49 times as large as when the vaccine is given than when the placebo is given. And so what I'm doing here then is essentially, in the way that we had defined it in our tables, polio-free is the failure. Okay? Group 1 is the vaccine. Group 2 is the placebo group. So going back to some of my previous stuff, that's where that's coming from. I'm essentially using this as interpretation of the odds of a failure. Okay? Now, one reason why I do this is because I showed you basically four, essentially, in terms of a base way, 4 different ways to interpret the odds ratio. Now, I would think that probably what would be more of interest for researchers when they would actually state it in their paper is that, they're very concerned about knowing, is this vaccine working? Is it reducing the incidence of polio, essentially? Or you can think of it this way, I want to know how my probability of being polio-free is increased by taking the vaccine rather than the placebo. So in this particular case, notice how I phrase it in terms of essentially your chances of being polio-free. Or specifically, I talk about the odds of being polio-free are higher if you take the vaccine than the placebo. So I think this is probably the preferred interpretation. I think someone who has a decent background in statistics will still get the same meaning from looking at it this way. But I think that they would probably prefer the second. Or you could also do it the third way. The estimated odds of contracting polio are reduced by 60% when the vaccine is given instead of the placebo. So that kind of talks about some of the, there was a question earlier about phrasing the interpretation this way as well. I don't think I used the word reduce. I think lower maybe, something like that. And well, where does that come from? Well, right here. So 1 minus 0.4 is the 60%. And you could also do similar interpretations in terms of the odds ratio. The key thing is, notice the odds ratio does not contain 1. So what we have proven with this clinical trial is that, yes, there is something going on here, that this vaccine is reducing the incidence of coming down with polio. Okay, any questions? Like I said, odds ratios will be popping up all over the place this semester. So there's 2 more sections in 2 more subsections in section 1.2, which I am going to skip over. You're welcome to read it, but you're not responsible for it. Really briefly, the matched pair section. This allows you to look at a 2x2 table in a different way, where basically what we have been saying is that row 1 corresponds to 1 binomial distribution. Row 2 corresponds to 1 binomial distribution as well, and we are interested in comparing pi 1 and pi 2. Another way to view this table is in terms of multinomial counts. So I think most of you have probably seen a multinomial distribution. If you haven't, don't worry about it. We will in chapter 3. But if you have, you can think of the 4 cells in this contingency table as representing 4 categories of a multinomial distribution. 4 counts from a multinomial. And the reason why you want to view the data in a different form, in this particular case with a matched pair sample, is that you're not necessarily interested in looking at pi 1 minus, you're not interested in looking at pi 1 and pi 2 anymore. Instead, what you're interested in is this, where are essentially marginal probabilities. So, for example, suppose you have 2 different tests that can be used to detect HIV in an individual. Okay? You have the standard test, maybe we call it a gold standard test, that you know by past results that this is the most accurate. And you want to compare that to some new test that has been developed to diagnose HIV in an individual. Okay? And so what you like to know then is, well, what's the probability that my standard test gives me a positive result? And what's the probability that my new test gives me a positive result? And compare those 2 probabilities directly, maybe through a difference, maybe through a ratio like we did with the relative risk, and so on. And so what that basically represents then is that this probability the standard test is positive is a marginal probability. In other words, you're finding you don't care about the new test at all. You want to know what's the probability of positive only. Probability of a new test is positive. That corresponds to that marginal probability there. Now, because you're dealing with those marginal probabilities, basically what ends up happening is you have what's very similar to matched pairs in a t-test situation where you're comparing two means, that essentially, you can think of like the same blood sample is being tested by the standard test and also the new test. So thus you're getting like a matched pair of observations. And there are ways that you can make this comparison. Take a look at this section in my book if you're interested. And of course you can have larger contingency tables than 2 by 2, and we will talk about those in chapters 2, 3, and 4. In chapter 2, what we will do is say, okay, suppose you still have a success or failure. So you still have 2 possible response outcomes, but maybe now you have a large number of rows. Okay. And then in chapter 3 and chapter 4, we'll say, well, you could still have a large number of rows, but maybe now you have a large number of columns too. So instead of having 2 possible responses, like success or failure, maybe you now have 3 possible responses, let's say low, medium, and high for something you're measuring. How do you handle those? That would be chapter 3 and chapter 4. We had to use different probability distributions for that. Okay, are there any questions? Okay, let's get into chapter 2 then. So analyzing a binary response, part 2. So what we've done in chapter 1 was simply look at, you have one binary response variable, and you're interested in what's the probability of success. And then we went into a situation where you have 2 binary response variables. You wanted to compare the 2 probability successes. So chapter 2 then generalizes it to essentially as many as many, let's say, groupings as you want. In fact, if you have a sample size of n, let's say, you could have n groupings. Now, rather than looking at the stuff in terms of a contingency table, what we will typically do is instead put everything into a regression model context. Because you can think of your independent variable, also known as an explanatory variable, also known as a covariate, your x often in a regression model, essentially as denoting what group you're in, like your row number to some respect, or your row that you're in a contingency table. So let's begin by reviewing a little bit regression models, just to make sure we're all up to speed. You should have all seen regression models at least a little bit before in the Stat 801 course. A regular old normal linear regression model looks like this, where your response variable is y. I put a subscript I there to denote which observation we're talking about. We can have up to n possible observations. Then we have a y-intercept term called beta 0. This is a parameter that we will want to estimate. And then we incorporate what these x's. I will call them explanatory variables because their purpose is to explain information about the response. A lot of other people call them independent variables. Then we have our explanatory variable x. So we have the first one. That's why I have a subscript 1 there. It's for observation I. And the amount of effect that x has on y then is measured by this parameter beta 1. So notice if beta 1 is equal to 0, what does that say? Well, basically x1 is not affecting y. If beta 1 was equal to 0. If you take 0 times x1, what happens? You get 0.
0.
Okay. So that means x1 is not going to have an effect on y. So if beta 1 was positive, what would that mean? As x increases, what happens to y? Generally speaking, it increases. So if beta 1 was negative, as x1 increases, that means essentially y is going down on average. You could also have x2. You could also have all the way up to, let's say, p explanatory variables. So how many betas do I have? P plus 1. And then also with the normal linear regression model, you have this error term. It's called epsilon. Epsilons are distributed independent. With a normal distribution, means 0, variance sigma squared. Notice that this variance there does not have a subscript on it. So that means we have constant variance throughout. That's an assumption of the model. You could also look at the model like this. And I think actually in terms of what we're going to be doing, it's better to look at it like this. look at the expected value of y. So what would you expect y to be on average? Well, just take the expected value here and do the same thing over here. We're going to treat the x's as constants. The betas are constants because they're parameters. The only random variable is epsilon. What's the mean of epsilon? 0. So that's why you only have this linear combination of the betas with the x's there. So what this essentially means, and this is why I think it's good, at least in the context of our class, to think of it like this. What this means is that you're saying that your y's are distributed independent with a normal distribution of a mean of the linear combination of the betas and the x's and a variance of sigma squared. Because x's and betas are constants. If I take the variance of this guy here, the only thing I have to worry about is epsilon. So what's the variance of a constant? 0. Okay, so that's the assumption of a regular old normal linear regression model, is that you have that. And so notice how my mean can change as a function of explanatory variables. In fact, I could have a situation where none of my observations have exactly the same mean. So that's nice because it allows you to, be very general. So let's talk about now regression models for a binary response, because that's what we have. So since I have a binary response, my y's now are going to have a Bernoulli distribution to them. And we'll still say a 1 denotes a success, a 0 denotes a failure. These y's are going to be independent of one another. And the mean of each of the y's is going to be pi sub I. So the mean of the expected value of y1 is pi sub 1. Expected value of y2 is pi sub 2. So before, we didn't have that subscript I there, all the way back in section 1.1. We had a constant mean. And then in section 1.2, we said, well, we had potentially two different means, either group 1 or group 2, pi 1 or pi 2. Now we have up to n different possible parameters. Well, we do have n different parameters, I should say. So that means you have n different parameters you need to estimate. Before, we've only seen at most 2 parameters, pi 1 and pi 2. Okay, but we can simplify things here so that we don't have to worry about n different parameters and have to estimate them all separately. You should think about, especially if you're a set major, think about what the maximum likelihood estimate would be if you did have n parameters. You're observing either y equal 1 or y equals 0. Think what pi hats of I would be if you had to treat it like that. So here's my regression model now. Expected value of y sub I is equal to beta 0 plus beta 1 times xi1. If I want to, I could add more explanatory variables. I was just trying to write it in a more easier form, just as an introduction. This expected value of y sub I is pi sub I. Again, the mean of a Bernoulli is the probability of success. So what we're doing now is we're going to relate our explanatory variable. Let's just think of x1 now, because it's just easier to say. We're going to relate our x1 to the probability of success now through this linear equation that's now dependent upon not n parameters, but just 2. Beta 0 and beta 1. That's it. So we have simplified this. And this is actually somewhat, to some respect, an assumption. We're assuming that this probability of success is dependent upon one explanatory variable x. And the way it's dependent upon it is in this nice little linear form. Do I think in the real world it happens exactly like that? No. All models that we have in statistics are approximations for reality. And what we're just hoping is that this is a good approximation. It seems reasonable. One way to think about it, and we'll talk about this shortly, suppose x was the distance of a field goal, and pi was the probability of success. So if you want to understand the relationship between the distance and the probability of success, perhaps it's a nice little linear relationship. You know, as you know, what would you expect? Would you expect beta 1 to be positive or negative? Negative, because as the distance of a field goal goes up, it's probably going to be more difficult to make, so the probability of success goes down. And so again, that's an assumption, but it might be it seems reasonable to do that. And you might be thinking, well, how good does it work? Well, we can look at measures to evaluate the model. If you've ever heard of goodness of fit measures before, we're going to look at how good this model fits the data. So that could be that's our model. This is how we can get around having to deal with n different pi sub i's. We're going to simply say the pi sub i's are a function of x and just two parameters. Or to be more general, maybe p plus 1 parameters, if we had maybe additional explanatory variables. Now, to estimate these parameters, we don't want to proceed in exactly the same way as you would do with normal linear regression models, or work with it exactly the same. First of all, you know, with a normal linear regression model, it's called normal because y sub I has a normal distribution to it. Here we have a Bernoulli distribution. Okay, so that's one big difference. Also, the variance of a Bernoulli random variable, remember it's pi times 1 minus pi. And now since we allow the pi's to be to change for every observation, look at my variance changes. And so now I no longer have my constant variance assumption that you had to have before with normal linear regression models. So what we're going to do then is use maximum likelihood estimation to find parameter estimates. Here's my likelihood function now. You know, think of it in terms of what you saw in section 1.1. Before in section 1.1, we had one parameter, it was pi. Now I have two parameters, beta 0 and beta 1. It's a function of my data. So given my data, I want to find what the maximum likelihood estimates for beta 0 and beta 1 are. But the stuff that's on the right-hand side of the equality there is essentially the same as what we had. We take the product of a whole bunch of Bernoulli distributions. Or, in other words, the probability of successes, I should say. I'm sorry, I didn't say that very well at all. You're taking the product of what ends up being Bernoulli distributions, yes. You know, if y1 is observed to be a 1, of course, you're going to put a pi there. If y1 is observed to be a 0, you put a 1 minus pi there with the corresponding subscript. So that this, then, is my likelihood function. Exactly the same as we had in section 1.1, except for the subscript I. In this pi sub I, what you need to do is plug in this linear function. I don't do it because it's more compact like that, and I can draw comparisons a little bit more easily to section 1.1. That's my likelihood function. I could find maximum likelihood estimates. Fortunately, though, there's still a problem. Could you find a beta 0, beta 1, perhaps an x, such that pi sub I is negative? Or pi sub I is greater than 1? Just start plugging in values of possible values of beta 0, beta 1, and x. You could have unrealistic estimates of your probabilities. We need to fix that. So that's where, instead of using a nice little linear form for a regression model, we're going to use something called a logistic regression model. This is the most frequently used type of binary regression model out there. I say binary meaning that's describing my response. We'll a little bit later look at what are called probit regression models. We'll look at complementary log-log models as well. But primarily, logistic regression models are the most common type of binary regression models. So that's why we'll spend most of Chapter 2 doing that. So this is what my model becomes with what's called the logistic regression model. And you'll see why it's called logistic at the end of chapter 2. It's just, it takes some explanation. So I think it's best to talk about at the end of chapter 2. So just be patient. So this is what my logistic regression model looks like. So now you see the exponential function coming in there. But I still have this linear combination of the betas with the x's, just like I did before. The reason why I'm using this transformation of them is because now this transformation guarantees that pi will always be between 0 and 1. Well, why? Can someone tell me why it can't be negative? I hope I don't have the answer up there. No, I don't have the answer. Why can't this be negative?
The numerator is always positive, and the denominator will also always be positive.
Because of the exponential function. Yep. And then why is this always less than 1? Well, take a look what's in the numerator and take a look what's in the denominator. Same thing, but the denominator also has 1 plus it. So this has to be less than 1 always. So this is what guarantees us my result from my model to always be between 0 and 1. Now there's another way that you could write this model too. How about on just the right-hand side, you make sure that only that linear combination of the betas and x's is over there. On the left-hand side, then, you allow that to change. So you just do some algebra, and this is what you get. The natural log of pi sub I over 1 minus pi sub I. Make sure you can go walk through the algebra and show that. Actually, I've even given that as a problem on a test before. But what's really cool is this. What's the stuff inside this natural log part here? Pi sub I over 1 minus pi sub I. What's another name for that? Odds of success. So what we're doing is we're relating the log odds of a success to a linear combination of my betas and my x's. So you might be thinking, that's kind of cool. And also what this is going to allow us to do is then use odds ratios to compare the effect of, let's say, x at a value of 1 versus x at a value of 2. We'll find 2 different odds and take the ratio. We have some nice mathematical simplifications that occur also with that. Now this transformation that we just saw on the left-hand side, this natural log of the odds of success, actually has a name that's commonly used. And I will use this too. It's called the logit transformation of pi. You can get some idea of where that's coming from. You have the log up there, and you have the log of logit in that name. There's actually more to the naming convention there that corresponds to what are called probit regression models. We'll talk about that more later on in this chapter. Now, the stuff that's on the right, and also, I should say, this naming convention, calling this the logit transformation, leads to a third way to write your model that's even more compact. The logit of pi sub I. Put that on the left-hand side, right-hand side, linear combination of the betas with the x's. Now, this linear combination of the betas and x's is also referred to a particular name. It's often referred to as the linear predictor, because it's a linear combination of the betas and the x's. That's just where it comes from. So this is the linear predictor. Commonly used terminology. And then lastly, I could also write my model where I just simply drop off the I subscripts, where it's just assume that you're talking about that, each of the pi's could be potentially different depending upon what the explanatory variables are. One problem with that is that this kind of leads to some notational ambiguity, because I used just pi before in section 1.1, But I think in the context of what we're doing, it will always be clear that, okay, we're working with a logistic regression model. So the pi's change as a function of x's. So that's why I'm comfortable with dropping the I subscript there. I hope you will be too. So let's take a look at a plot of the model. So my corresponding code is in pyplot.r. And let's just say that I have one explanatory variable x. I'm going to let beta 0 be equal to 1 and beta 1 to be 0.5. A plot of pi versus x is shown on the left-hand side here. Okay. So pi on the y-axis, x on the x-axis, or x1 on the x-axis, if you want to say it that way too. Notice first of all, of course, the probability of success is always be between 0 and 1. Oops, if I can draw the straight line across. It's always be between 0 and 1. Notice how that curve kind of looks a little bit like an S. A little bit. Also notice how the slope changes as a function of x. So you can see the slope is smaller when pi is closer to 0 and closer to 1. And then in fact it reaches its maximum point at pi equal 0.5. Also notice that as x increases, pi increases. We have a positive relationship because beta 1 was positive. Well, what happens then if I let beta 1 be negative 0.5? Well, then the curve goes down. Now we have a negative relationship. So as x goes up, probability of success goes down. Again, that's something that you would expect if we were talking about field goal kicking and x was the distance. Also notice that if I were to draw a line at pi equal 0.5 across these plots, essentially the top portion of the plot will be like almost like a mirror image of the bottom portion, and vice versa. Okay? Any questions about what this looks like? On page 2.8, actually I even put what the slope of the line is. You can use some simple derivative with some using calculus and find it. How did I find this plot? I want to make sure that you understand so you can do plots like this on your own, because you will sometime in the future. So let's just spend a little bit of time talking about that. And unfortunately, I did not actually get my program out. Let's see. Don't want that one. Okay. Just a second. So first of all, what I do is I use the par function to basically partition my plot into two different subplots, you could say. The par actually stands for graphics parameters, and there's a variety of different graphics parameters available to you in R. In particular, there's one called MFRow. I don't think we've talked about MFRow. Correct me if I'm wrong. Have we talked about MFRow?
We showed in our linear regression video for practicing with R. That function was there.
Okay, okay. Well, then as a review, MFRow means make frame by row. And the first entry is going to be the number of rows. The second entry is the number of columns. So all this does, if you think of it as like a table structure, it's going to be one row, two columns. So in my first plot then, I'm going to put then the plot with beta 1 equal 0.5. So I'm going to set beta 0 to be 1, beta 1 to be 0.5. Actually do that. And then I use the curve function. I believe we have seen the curve function before, at least in the introduction to R video. And basically what that means is I need to put in my function that I want plotted, written in terms of something called x. So all I do is I take the XP function, beta 0 plus beta 1 times x, divided by 1 plus the XP function, beta 0 plus beta 1 times x. So what R does, it puts by default 101 equally spaced values of x in there, where they are spaced between negative 15 and positive 15. And then I did some more fancy stuff with my title and also my my x-axis label, y-axis label, so I can use some Greek fonts to use some fractions. Don't worry about that. You don't need to use those if you don't want to, but it can make your plot look nicer. And there is my first plot. And then I just do a similar thing for the plot on the second column as well. Okay, so I got some questions on the bottom of page 2.8. So let me do some erasing too. So what's going to happen to this first plot here with beta 1 equal 0.5? If, let's say that beta 1 was increased, maybe it was 1, 3, 100. What's going to happen to that plot?
We'll get steeper.
Steeper, yeah. So in other words, you know, maybe instead you might have something that looks like, if I can draw it well, basically you're going to rise up to pi equal 1 faster, because now you have essentially a stronger relationship between x and pi. What's going to happen if beta 1 goes to 0? So let's say you're at 0.5 and you start decreasing beta 1 so it gets closer and closer and closer to 0. So think of it like in linear regression. Your slope is 0. And essentially you have a flat line across your plot. And essentially the same thing will happen, essentially. The same thing will happen here. You can think of it as, this is going to be stretched out more. This is going to be stretched out more. So it's going to take longer to get up to pi equal 1, if you think of it in terms of increasing x. And then lastly, suppose you did a plot of logit of pi versus x1. What would that look like? Would it be a curve like this? Think beta 1 equal 0.5 if you want a beta 1. So here's x, here's logit of pi. I want to do a plot. What's the shape of my line that I'm going to draw? It's going to be just simply a straight line. Because remember, logit of pi is equal to beta 0 plus beta 1 times x. It's a linear function here. Okay, that takes us to page 2.9 then. We're going to talk about how we can estimate the corresponding parameters. So as I was saying before, we're going to use maximum likelihood estimation. Here's my likelihood function written in terms of, in general, for let's say p plus 1 betas. And each of these pi's then are represented here as this transformation of a linear combination of the betas and the x's. And so, similar to what we did in section 1.1, you could find the log likelihood function, and that's what I did there. You can see that's starting to get kind of messy. You could do some simplifications with the log likelihood function. And then if you were to use, let's say, stat 883 stuff, for those of you who have taken it or will be taking it, what would you want to do next? Take the derivatives with respect to beta 0. Take also a derivative with respect to beta 1 of the log likelihood function. And do that for all the betas, so that you have essentially p equations. Set each of the equations equal to 0, solve for the betas. That's how you would get the maximum likelihood estimates. That's just like what we did in section 1.1, except for we only had one parameter to worry about, the pi. Okay? Now, Perhaps you're thinking right now, geez, I never want to have to do that on a piece of paper. Well, you're not going to have to. First of all, there's usually not a closed form solution that exists. Meaning I cannot write out, similar to what you would have with like normal linear regression model, I cannot write out beta hat 1 is equal to, like, say, the sum of the x's times the sum of the y's. I can't do that. There's not a closed form solution that exists in general, except for some specific special cases. And so what you have to use are what are called numerical iterative methods that for any particular data set that you have, that will essentially search for what the beta hats, your maximum likelihood estimates, in case I didn't say that, to search for what your beta hats would be. Okay? Fortunately, R does this automatically for us, so we're not necessarily going to have to look at the details. In Stat 971, if you were to take that course, you actually, I believe, get an actual opportunity, think of it as an opportunity, to actually program it in by hand that will allow you to get a better feel for the numerical iterative method. Okay? I do want to talk about a little bit about what numerical iterative methods are, just to make sure you guys understand. Okay. The actual numerical iterative method that's usually used with logistic regression is what's called iteratively reweighted least squares. And basically, if you've had a Stat 870, a full semester of regression analysis, you've heard of weighted least squares before. And essentially what this is weighted least squares, but done in an iterative format. So it keeps on reweighting, or keeps on creating new weights over and over and over again until you have what's called convergence. So what happens is this. Suppose you come up with some initial estimates for what your beta hats should be. Maybe you just did simple normal linear regression. Okay? Somehow you come up with some initial estimates. And then what this iteratively reweighted least squares thing does, this numerical iterative method, it tries to find better estimates. So let's say it finds some better estimates. Let's call it beta hat 0 with a superscript 1 to indicate this is now the first iteration, all the way down to beta hat p with a superscript 1. And then it compares these two. If they're very, 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 very close, what that says is my better estimate that I've just gotten is essentially what I had before. So I must have the right estimate. And I have what's called convergence occurs. If instead my beta hats are somewhat different at iteration 1 than what they were for iteration, let's say 0, what I started off with, then it says, uh-oh, things are changing. Maybe I can even get better than what I just did at iteration 1. So let's go to iteration number 2. I guess I don't have beta hats for 2 there. So get beta hat with a superscript 2. And again, compare at iteration 2 to iteration 1. If they are very, very close, it says, oh, this better estimate that I got was about the same as what I had before. So therefore, I must have my maximum likelihood estimates, and I have converged. If they're not the same, go to a third iteration. And keep on going until you get to a point where you have convergence. That's how this numerical iterative method works. Generally speaking, it always works. It finds the maximum likelihood estimates. But at times you can have problems. And that will be discussed towards the end of chapter 2. So until then, just think that we live in the perfect world and everything's going to work out for us. The actual function R that automatically does this for us is called GLM. The LM stands for linear model. You saw that in the introduction to R section. So you can think of, that linear combination of the betas with the x's. That's essentially a linear model. The G stands for generalize, because we're not just doing normal linear models anymore. We're generalizing to allow for a Bernoulli response. So that's where the name GLM comes from. So let me ask you a question, though, and this will be the last time we talk about this numerical iterative procedure or method until later in chapter 2. Suppose, well, with any kind of numerical iterative method, you have to have like a maximum number of iterations, maybe 10, let's say. Let's just say it's 10, because you don't want to keep on going over and over and over and over and over and over again, trying to get better estimates, because maybe there's a chance you might not even find them. So let's say you reach the maximum number of estimates or iterations that you have specified. It's 10. You reach that. You have not converged. Do you think you should use your beta hats? No, because that next iteration, they could change. And remember how important these beta hats are to us. They allow us to interpret the relationship with x and pi. Or you can say equivalently x and y. So if your beta hats change, that says your interpretation will change. You wouldn't want to use any kind of model that has parameter estimates in it that had not converged. Okay. So let's take a look at an example then to see how we can estimate these models. This is an example that we will be dealing with through all of Chapter 2. It's one of my most favorite examples. It deals with place kicking in football. So, in football, we've seen a field goal attempt, but also there are what are called point after touchdowns. They're worth 1 point if successful, 0 points if failure. Typically, point after touchdowns, or PATs, are done from a distance of 20 yards. Not always, but typically they are. And so a place kick then includes the possibility it's either a field goal or PAT. Okay? So that's why I call this my place kicking example, because I'm going to look at both field goals and PATs. This was actually, I think I kind of talked about this before. Have I talked about this before in this class? I apologize if I. Okay. So for the creative component of my master's degree, when I got my master's degree in 1996, I had to do like what's called a report. In our department here, we call it a project. And basically what this amounted to was a 120-page document that I wrote out about place kicking in the NFL, trying to figure out, well, what factors affect the probability of success? Obviously distance, but what else? And so that was my goal. And so what I actually did was I collected data on all possible place kicks that had happened during the 1995 NFL season. The corresponding, so that's what I did for my master's degree. I worked on it a little bit more, and I got it published in a journal called Chance. Basically, if you've heard of like the Scientific American magazine, this is the statistics equivalent of it. So it's something that, as long as you've had like a Stat 801 course, you can get something out of. So it's a nice publication. But you're not going to get tenure by publishing in Chance. Anyway, so this is the information then that I collected. The week of the season, the distance of the place kick, change. It was a binary variable denoting, was it a lead change place kick or a non-lead change place kick? What that means is, let's say the score was 10-7, where the team that was kicking a field goal had 7 points. Well, if successful, the score would be 10-10. So there was a kind of a lead change. Now the game's tied. So change would be a 1 in that situation. If instead I had 10-6, then it would be not a lead change place kick. Because now it's 10-9, and the team that was kicking is still behind. If it was 10-8, it would be a lead change place kick. Because now the team that was kicking would be ahead. If it was 10-10, it would also be a lead change place kick. So why do you think I'm looking at change? What do you think that's maybe trying to measure? Pressure, exactly. Now, how do you measure pressure? Do you go out and ask the place kicker, do you feel pressure or not? Well, you can't do that. So that's what I'm using in place. Another way that you can measure pressure is the time remaining in a half of a game. And so I have elap 30, which is the number of minutes remaining before the end of the half. 0 if it's an overtime. My PAT variable is a 1 if it's a PAT, 0 if it's a field goal. Type, binary variable denoting dome versus outdoor. So you would think that place kickers would prefer to kick in dome stadiums because you don't have to worry about weather. Field, grass is a 1. Artificial turf will be a 0. Again, you think place kickers, generally speaking, would prefer to kick off artificial turf because grass, there's various issues that you would have to worry about. Like, let's say if the grass was wet, maybe it might be muddy too. And then wind, finally, we'll end with this. A binary variable for place kicks attempted in windy conditions versus non-windy conditions. where I decided to use, I think it was like the 10th percentile, which was 15 miles per hour. Now you might be wondering, why don't I just use the actual number itself, the wind speed, I should say. I know I'm almost out of time here. I'll do this real quick. The problem is, what's the wind speed inside of dome stadiums? Is it 0? No, there's air circulation going on there. Especially if you're a Minnesota Twins fan, and remember when they used to play up in the Metrodome. You know, supposedly it's a legend that they would turn up the air conditioning when the opposing team was up at bat, because that airflow from the air conditioning would try to keep the baseball from being a home run. In terms of, it would be like having like a wind blowing into the stadium. So because of that, and in fact one stadium did tell me what the wind speed was, one dome stadium did tell me what the wind speed was, but all the other ones didn't say anything about it. I was concerned about, how do I handle this? So I thought, okay, well, why don't we just make it a binary variable? Windy versus not windy. I don't think it's windy in dome stadiums, so I thought felt pretty confident that if I used that cutoff at 15 miles per hour, I'd be okay. And so, I had to make a decision. These are the kinds of decisions you have to make with research. So I'll end with this. At the time, I didn't have information about orientation of a stadium and how, like say a north wind might affect something more than a south wind or west wind or east wind. I didn't have that information at the time in 1985. Now most stadiums are oriented north-south, but not necessarily all. And also, wind swirls in stadiums too. And so even if the wind's out in the north at 15 miles per hour, is it really then on the playing field? And so I had those kinds of issues that I had to deal with. Those are real issues that you have with research. One last thing, my response variable, I'm going to call it good. It's a 1 for success, 0 for failure. So sorry I went over there. Are there any questions? Okay, that's it for today.